Today I'm going to talk about nanoplasmonics for enhanced light matter interaction. And specifically, I'm interested in applications to sensors and spectroscopy and optical manipulation. So I'm going to focus on those three aspects in this talk. Okay. So we've done a lot of work on the so-called nanohole arrays, which allow for the effect of extraordinary optical transmission. So just a show of hands, who's heard of extraordinary optical transmission in this room? Okay, a handful of you. Essentially, this phenomenon refers to the situation where you have hole arrays in a metal film. These holes by themselves are supposed to only transmit a very small amount of light, but if you arrange them in an array, all of a sudden you can get very large resonant amounts of light going through this hole array. And so we've been using this geometry for basically sensor devices. And I'm going to review nanohole surface plasmon resonance. SPR stands for surface plasmon resonance. So it's basically a resonance sensor platform. And I'm going to talk specifically about some of our innovations. In particular, I want to focus on these two innovations which are fairly recent, which relate to flowing fluids through the nanoholes. So not only are these conduits for the light, for the electromagnetic radiation, but they're also conduits for the actual fluid. So it's combining nanoplasmonics with nanofluidics to get a double benefit, okay? So I'm going to talk about how we can use this to get preconcentration, and then I'm going to talk about some of our older work, but stuff that we're trying to develop more towards actual a sort of a lab-on-chip type of device, okay, or platform, okay? So just to review, for those of you who don't know what surface plasmon resonance is, if you have a metal film like gold, it permits wave guiding of an electromagnetic mode that's bound at the surface. This electromagnetic mode is basically light that's exponentially bound, tightly bound to the surface, called a surface plasmon polariton. Because it's a waveguide mode, essentially the light stays in the waveguide mode, okay? It's like an optical fiber. Light doesn't leave the optical fiber. So if you want to get light inside the waveguide mode, you have to use something like a prism to match to the wave vector of this waveguide mode. And so this is what this prism is doing. It's allowing you to get light from free space into this waveguide mode on the surface of a metal film, okay? Now you see I've added a surface layer here, and the surface layer is typically something that you want to sense. So you bind some proteins or molecules on the surface of this gold. And this allows you to, because this waveguide mode is so tightly bound to the surface, this allows you to monitor changes in the properties of the waveguide mode. And so you can monitor this by looking at the reflected light, light that couples into this waveguide mode and gets reflected out on the other end. You can detect it over here. And you can monitor the binding of proteins to surfaces like this. This is what the waveguide mode looks like. So this is the magnetic field of the surface plasmon polariton. This is the gold, and this is the dielectric. You see the magnetic field is decaying both into the dielectric above and into the metal, and its wavelength is smaller than the wavelength of light, which basically says that you cannot just directly couple light into it. You have to use a prism. Okay, so this is what, if you look at the reflection of light at a single frequency as a function of angle here, you'll see a dip in this reflection as a function of angle. And this dip in reflection basically comes from the coupling of light into this waveguide mode on the surface, okay? And if you change the surface properties by adding, for example, an add layer of dielectric material like a protein or something, then you'll get a shift in the position of this dip in the angle. And this is what people use to sense. They look at the shift, and that's how they use their sensor. So this platform is very simple. It's just a simple gold layer, single gold layer, and it's a commercial platform. It's been developed by Biaxial, is probably the biggest player in this area. But there are some smaller custom devices that are basically handheld versions of the surface plasmon resonance platform that can be used for sensing many different things. Okay, so it's a general sensor platform. So we are looking at extraordinary optical transmission as a platform for surface plasmon resonance. And like I said before, extraordinary optical transmission refers to the situation when you have holes in an array in a metal film. You see resonant peaks in the transmission through these holes. Okay, so this is the optical transmission as a function of wavelength through this hole array. This was discovered in 1998 by Eberson's group and co-workers. Okay. I'll just skip that slide. But the most important thing here is that the resonance peak that you get from this film is basically the resonance peak will depend on the dielectric material that you have close to the surface of the film. So it can also be used as a surface sensor just by looking at the change in the resonance peak. So we wanted to combine this extraordinary optical transmission with surface plasmon resonance in a single, combining these two ideas together to do a surface-based sensing. And so we were really the first people in 2004 to actually demonstrate surface-based sensing using the nanohole arrays. And so what you have is a bare gold over here. You attach a monolayer, and you see a shift in the transmission peak. And you attach a protein on top of that, and you see another shift in the transmission peak. So you see, you can sense the absorption of a monolayer and of a protein by just looking at the transmission through these hole arrays. Okay, so this is how it is used as a sensor. So this is pretty old stuff. What's really interesting about this particular geometry, as opposed to the prism geometry that I showed you before, is that here you just need to have light transmitted directly through a flat gold film. It's a collinear geometry. It can be sit in a microscope setup very easily. We just image the transmission of light through this gold film. And on top of this, we can add a whole bunch of microfluidic functionality. So we can flow in different types of fluids. We can mix fluids. We can do some reactions. We can do multiple binding steps. So this allows for a lot of functionality in the context of biosensors. Okay? So this is what's really made it interesting for us. And you can read one of our earlier review articles on the microfluidics and combining the microfluidics in surface plasmon hole arrays. There are many other research groups worldwide that are working on this particular platform. Most of these groups are recognizing the same. This is by far not a complete list, but this is just a very abridged list of the different people that are working on this. But most of them really recognize that this platform can give very good sensitivity. This is a curve of basically the sensitivity that you expect to get in terms of refractive index units. You're down to the 10 to the minus 6, 10 to the minus 7 level. So you're getting close to what the biaxial system can do, what the best commercial systems can do right now. This shows you that you can integrate these hole arrays into very dense arrays, and so you can do highly multiplexed sensing. So you can sense many different molecules or many different sort of analytes on the same chip. And so these single cells of hole arrays can be the size of only a 1 micron or 2 microns across. Okay, so it's very densely packed. Okay, so that's part of the capability here. Okay. So I wanted to focus a little bit on our recent innovations in this area. And one of our innovations was to actually use these holes not only as conduits for the light, but also as conduits for fluid. So combining the idea of nanoplasmonics with nanofluidics. Okay, so here we have a silicon nitride membrane. And on top of the silicon nitride, we have some gold. And we use focal time beam milling, which is basically a milling procedure to create nanoholes. We can mill holes through both the gold and the silicon nitride. So essentially, we have a freestanding membrane that's about 100 nanometers thick and a gold layer, which is about 100 nanometers thick. And we mill through both of these. And so now you can flow fluid through the holes. Okay? And just to show you how this works, this is an illustration of fluorescein dye under pressure. When we apply pressure to one side of the hole array, fluorescein dye streaming through. So you can see that this is actually, these channels actually allow for a lot of fluid transport, okay? It's vivid demonstration of streaming under pressure. Okay, I can just show that. So this, okay, I guess it doesn't want to show it again. Okay, so why is this useful? Well, the main reason I think this type of combining nanofluidics with nanoplasmonics is useful is because it removes some of the traditional diffusion bottlenecks to these sensors. Okay, so these surface-based sensors, the way that they work is you have an analyte that you want to detect, and you have to wait for this analyte to get to the surface. Okay, and in a channel that's 20 microns high, in a typical microfluidic channel, the time that it takes the molecule to get to the surface can be quite long. And if it doesn't make it to the surface, it's just flown away. So it goes off and we lose that molecule. So we haven't made use of that molecule. And So you're basically limited by this diffusion time, and even if it does get to the surface, it might not bind. It might leave again, and then you have to wait for it to diffuse back to the surface again. So with the flow-through platform, essentially what we do is we force all of the fluid to go within 100 nanometers of the gold surface. So the diffusion time is very short. It doesn't take a long time for the particle to get to the surface. It's basically at the surface already. And so by forcing all of the fluid right to the surface, you're removing the diffusion bottleneck. And so you can get orders of magnitude, or at least 1 order of magnitude improvement in the rate at which you sense. It speeds everything up. Also, you can get more capture because you don't have as much of your analyte just flowing over and being lost. Okay. These are just some calculations showing that in typical systems, considering the time constants associated with typical biosensors, that we expect to get about an order of magnitude improvement in this diffusion bottleneck. So we expect our sensors to be about 10 times faster than typical biosensors, which is important because if something that used to take an hour or 2 hours will now take of the order of a couple of minutes. This is just showing some of our work. We're working with the BC Cancer Agency, their antibody research unit, and looking at some cancer-relevant markers. We're working on platforms for sensing them. Okay, so just to sum that up, essentially we combine in nanofluidics and nanoplasmonics to speed up the diffusion limited tests, and this allows for many exciting nanofluidic opportunities, which I haven't really talked about. There are other people working in this area now. Subsequent to our work in 2010, Hatice Altug from Boston University published essentially the same thing, except they didn't do the surface binding test. They just did a flow measurement. GE has patented, or they haven't patented, they've sent in an application as of September 2009 to actually do this flow through with single nanoholes, basically using the same type of technology, a suspended membrane with holes. So there are other people that are also recognizing the benefits of this flow through platform. Okay. So the second part I want to talk about is related to using this flow through for pre-concentration. This hasn't been published yet, so this is some of our newer work. Okay. On this is mainly the work of a PhD student in Dave Sinton's lab, who's mainly responsible for all of the microfluidics here. Okay. Here we apply pressure-driven flow through this whole array membrane, and then we apply also an electric field. And because the analyte, because the thing that we're interested in sensing, it is typically charged in solution. Okay, when we apply electric field of the right potential sign, what you end up getting is polarization of the metal film, and this polarization blocks the negative ions from traveling through the channel. And so what you end up getting is this huge pre-concentration of the analyte at the surface. And it's a really fast process. And to show this, again, we'll just show a video of this pre-concentration. So this is showing, again, some imaging from the backside of the array and looking at the fluorescence that's going through the whole arrays in the gold film. You can see a huge pre-concentration under applied bias. But there is no streaming in this case because the potential is stopping the fluid, the analyte from actually going through the holes. The advantage of doing this, okay, so this pre-concentration in like a minute, you can get 180 times more higher concentration at the surface than you have in the solution. So that allows for much faster sensing once again. Okay. So this shows you some examples of what happens when you do sensing for a whole array without this pre-concentration. And when you apply a pre-concentration bias, you get really fast sensing and a much larger shift because effectively you're sensing from a higher concentration. So that just shows you that it's effective for surface binding tests. Okay. And these simulations basically show that we're in the right, we understand the nanofluidics associated with this. We've also done some work to look at in-hole sensing. With in-hole sensing, a lot of people have suggested, including myself, that the main sensitivity comes from the the gold surface around the holes, but actually the gold surface inside the holes is also important, and you can get similar peak shifts just from binding stuff inside the holes themselves, because the hole is a transmission is a conduit for transmitting light through the gold film, and by changing the properties of inside the hole, you can get large changes in the actual transmission. Okay. With microfluidics, you can do a lot of things to enable. For example, here we're showing mixing of some solution, and you can do dilution to different levels using this mixing chip. So microfluidics, by combining the nanoplasmonics with the microfluidics, you can do a lot of you can add a lot of the microfluidic functionality that's required for, say, ELISA-based. This is ELISA-like mixing setup, where on chip you do all your reference calibration through this dilution chip, with each different channel referring to a different dilution level, and then here you have your sensing channel, which is basically you compare with all of these dilution channels, and then you decide what concentration you're operating at. When we first started working in this area, we had this vision of trying to create this type of biochip that you could essentially, it might be disposable, it's microfluidic. You have some PMMA-based biochip with the whole array in it. We thought about doing flow-through. This was back in 2004, 2005 when we wrote the grant application for this. This figure actually appeared in the grant application. So this is the vision that we had. You have some CCD detector, you have some light source, you have some fluid channels in and out. And so this is the vision that we had for a device that would actually make use of this whole array platform. And this is a prototype that we've built in my lab just recently. And the prototype is essentially got all of the elements of the original design, except we haven't done the flow through on the chip yet. We've also added another element. We've added a two-color LED. And the two-color LED, what it does is the green color will see an increase in the intensity of light through the holes when we increase the refractive index, whereas the red will see a decrease in the intensity of light. And by monitoring the green and the red together, we can get some spectral diversity. So essentially we can isolate some effects that come from noise or thermal drift from effects that are actually real, that are coming from the analyte at the surface, so from the refractive index changes. Sorry, that last one didn't hide. This just shows a binding curve for the red LED and the green LED again, standard surface binding kinetics. Okay, another way to get diversity, when you use a single laser, instead of using a red and a green laser, you can use the fact that the periodicity of the holes determines the wavelength that will resonantly transmit. So if you're polarized along the y-axis, your wavelength will be shorter than along the x-axis, because we have here a biaxial array, okay, where one axis has a shorter length than along the other axis. And with this biaxial array, one polarization will see an increase in the transmission. The other polarization will see a decrease in the transmission when we have some analyte, or we change the refractive index close to the surface. And recently we've actually tried to implement this in a more of an integrated platform, where we actually have a polarization modulator, and we managed to get to 10 to the minus 6 refractive index units types of resolution. Okay, so this shows you that the sensitivity of these devices is beginning to come close to the best commercial devices available. Okay, so that's the main thing. We're getting our sensitivity by employing some of these extra techniques. We're able to get good sensitivity close to the 10 to the minus 6 refractive index units limit of detection. Okay, the second part of my talk, I'm going to talk more about spectroscopy using these whole arrays, and then I'm going to talk about optical antennas as a way to do a spectroscopy. And so when we had these whole arrays, we actually we tried every different type of experiment that we could think of with the whole arrays, and one of them was fluorescence. So you change the periodicity of the whole array, and for some periodicity you'll get enhancement in the fluorescence of some dye that's put on the surface. So you can get enhancement factors, of the order of 1 to 2 orders of magnitude in the fluorescence. You can also, instead of using dyes, you can use quantum dots and put those on the surface, and you get enhancement factors in their emission as well, okay? Reductions in their lifetime, for example. So they have much faster emission, much more efficient emission. We also were interested in nonlinear optics with these hole arrays. We realized that if you can make a single hole, this is not doesn't really allow for very sharp plasmonic focusing. What you want is something that has some very sharp tips. And the simplest approach we could think of to create something with very sharp tips when you only have about 100 nanometer resolution with the focus ion beam milling machine is to bring two holes closer and closer together to the point at which they just meet. And when they just touch each other, then you create these sharp apexes. And this just shows you what these apexes do to the light. They funnel the light down into the region between the apexes, so you get this sharp focusing at these apexes. And I'll talk more about this a little bit later. So these apexes are really important to creating the local hotspot over here, which can be useful for things like nonlinear optics, where you have higher intensity. And this just shows you that. Here we have the second harmonic generation through a hole array of these double hole structures. But first we start with a single hole, and then we start with two holes that are, we take the single hole and we pull it apart to form two holes, but they are overlapping. But they're overlapping so much that they're not creating this really sharp apex. Then at the point that they just overlap by the right amount, we get this huge enhancement in the second harmonic generation. It just jumps up a whole bunch when they just create these sharp peaks, and then it goes back down again. So this shows you the effect of making these double holes just overlapping to the right point. Other people have been looking, including Dr. Blair, has been looking at second harmonic generation from hole arrays, more so than us. This just shows you one example from rectangular holes, which basically has the same idea. By having these great enhanced local fields, we can look at enhanced Raman spectroscopy. With Raman spectroscopy is a process, it's kind of like fluorescence, except you have excitation light, which excites your molecule to an excited state, but it's a virtual excited state. It's not a real excited state of your molecule. And so if the light just scatters elastically, this is just light scattering. It's light coming in, hitting a dielectric particle, and leaving. If there's some interaction with the vibration mode of the particle or of the molecule, then what happens is you can actually have light that you can absorb part of the energy from the photon, and the light that's emitted is going to have a slightly lower energy. Okay, so this is called Stokes scattering. And also you can absorb vibrational modes from the molecule, and this can give you light with a higher energy. And so this process is called Raman scattering. It allows you to, it's important because it gives you a molecular fingerprint of the molecule. By looking at the vibrational spectrum, we can basically identify different molecules. And so this is a way of identifying molecules, okay? The important thing as this relates to plasmonics is that Raman, you can enhance Raman with nanostructured metals, but you enhance both the incoming light and the scattered light, okay? So you get a double enhancement. And as a result, you basically get something that goes as the fourth power of the incident light, of the incident field. So whatever enhancement you can create in the local field, you can have as the fourth power. So whereas fluorescence is usually 10 orders of magnitude larger, for example, than Raman, if you can create a local electromagnetic hotspot that's 5 orders of magnitude larger than in the usual free space environment, then you can basically make Raman scattering more efficient than fluorescence. Okay? So you can detect Raman from single molecules. And that's really the holy grail of this field, is how to get reliable single molecule Raman. Now we did this Raman on the hole arrays, and we did see an enhancement. When we tuned the periodicity of our hole arrays to the laser source that we were using, we could see a peak enhancement in the Raman peaks that we saw from this molecule, oxazine. Okay. But then we didn't want to use. I'm jumping ahead. We also looked at using double holes for this, because the double hole again gives you a much higher local field intensity. And again, you see the same effect. As you make the holes approach each other, at some point, when they just touch in, you get the highest enhancement in the Raman scattering through these hole arrays. Okay? So again, it's a way to enhance the local field in a reliable way. But we didn't want to do Raman on an array of holes. We wanted to do Raman from a single spot because we want to look at single molecule Raman. We want to look at Raman from single isolated, be able to detect at the single molecule limit. So to do this, we thought of the structure where we have concentric rings, which basically focus light towards the center of this double hole. And the nice thing about the structure is it's circularly symmetric, rotationally symmetric, except for the hole in the double hole in the middle. If light is polarized along the x direction over here, it's going to excite these cusps, and it's going to excite this local field enhancement. If it's polarized along the y direction, it doesn't do so as much. And so by just looking at just comparing the Raman from light polarized along the x direction to light polarized along the y direction, you see a boost of 40% in the total Raman signal of this entire structure. And this 40% is only coming from the small amount of molecules that are located directly at the cusps over here. So we've seen a sensitivity. You can estimate how many molecules are there based on surface coverage. And we estimated in this system we were at a 20 molecule limit of detection. So we're basically seeing Raman from 20 molecules here. And so we're getting pretty close to doing single molecule type of Raman structures. So to do single molecule Raman, we explored this structure. Okay? So this is the cantenna. So the cantenna is a Wi-Fi, this is a Wi-Fi cantenna that's used for local area networks. Essentially, you have a coaxial feed that has a probe which excites a standing wave of this Pringles can. Okay? And the standing wave, you have reflection from this back end, and then this other end is open, so the electromagnetic waves are directed out. So that's what an antenna does. It has directivity. It forces the electromagnetic waves to go in one direction, right? And this probe is positioned at the peak of the standing wave to give the maximum excitation of the standing wave. So you get both directivity and standing wave enhancement for the waveguide mode, the electromagnetic waveguide mode of this antenna. Okay. We try to build this thing for visible infrared wavelengths. Okay. So in the visible infrared regime, everything gets shrunk down. Okay. So instead of talking about 10 centimeters, we're talking about hundreds of nanometers. Okay. So everything gets shrunk down to nanometer size scales. So instead of building a full Pringles can, we started with a single gold layer, back-end layer, as the back of our Pringles can as our reflector. And then we had another layer which is actually forming the body of the can. And in that layer, we put our little dipole feed, and we made this ring aperture. And what this ring aperture does is it basically creates directivity for the light. So what we're trying to do here is if you have a microscope set up which has some numerical aperture, it can accept all light up to some angle, then we are trying to make this antenna such that it couples into the same numerical aperture so that all of the photons that are leaving the structure go right into your microscope. Or for Raman, we're also interested in the other process, that all the photons that come down through your microscope go right into this feed gap and excite the Raman molecules that are there. So by using this antenna structure, we've designed something that's called directivity enhanced Raman spectroscopy. So or DIRS, it's basically we're using the fact that you get enhancements in the Raman both for the incident photon and for the scattered photon by directing the photon efficiently into our microscope. We get this double enhancement. So it scales as the square of the local field, or in this case, the directivity of the field. Okay, so this shows you an example of a typical Raman spectrum we get with the antenna structure and without the antenna structure. And without antenna structure here is actually, it's a bit misleading. Actually, it's even better than this, because without antenna structure, I basically mean without this ring. I have this antenna, I have this base ground plane, so all of those features are there. The only thing I've left out is the ring, okay? So without the ring, you get this really small, weak signal. The ring, which adds the directivity, which makes the photons go directly into the microscope, boosts up your signal by a factor of 10 around there, okay? So this just shows you what happens if you change the radius of the ring. There's some optimal condition, which is well suited which you can look at microwave theory, and it's pretty easy to figure out what the optical what the optimal ring size should be. Okay, so this is just showing you some of the directivity patterns that you expect from different structures. I won't go into that in too much detail. But this whole idea of optical antennas is quite an interesting area, I think. And it's an area that there's a lot of work that's being done translating some of the ideas from the microwave antenna regime into the visible infrared regime. And part of the challenge here is these ideas don't map directly, okay? What works in the microwave doesn't always work in the visible infrared regime. But the main concepts we're interested in are things like directivity and things like impedance matching. Okay, they've tuned basically the impedance of this antenna structure by changing the distance to a ground plane and having better radiation efficiency from this antenna structure. So these concepts, which are well understood in the microwave regime, there's still a lot of work to be done to figure out how they work well in the visible infrared regime. Okay, here's again directivity. So what a lot of people are doing today is just trying to take microwave antennas and turn them into the visible infrared counterparts. So this is a Yagi-Uda antenna, and this is showing this directive emission from a Yagi-Uda antenna that's built for quantum dots. So it's a sort of a single photon emitter that's highly directive, as published in this paper over here. But these concepts are not, what was optimal for the microwave regime is not necessarily the optimal design for the visible infrared. So I believe there's a lot of work to be done in that area. Okay, in the third and final part of my talk, I just want to comment on some of our recent work on optical trapping and manipulation. So optical trapping uses the scattering of light, and light has momentum. So if you have a focused laser beam focusing down to some spot over here, if a dielectric particle comes into the laser beam, it's going to scatter some of the photons out towards the side. That means that there's momentum going this way, okay? And as a result, there has to be a restoring force pushing the particle going. There's a momentum or an increase in the momentum of the particle towards the center of the beam. Okay? So the scattered photons going out this way push the particle in towards the center of the beam. So this is the so-called gradient force. There's a force acting on the particle that attracts it towards the highest intensity. This is the electric field. This is a gradient. The highest intensity part of the beam. Okay? There's a major problem with this approach to optical trapping. It works very well for particles down to about a micron in size. But it scales as if you talk about Rayleigh scattering or smaller particles, the scattering of the particle, the polarizability, scales as the third power of the size of the particle, of the radius of the particle. So as particles get smaller, it's very much harder to trap them. Also, their diffusion is a lot, they diffuse more easily. And so the trapping times will be decreased as well, which scales linearly with the particle size. This was recognized early on in this pioneering work by Steve Chu and Arthur Ashkin, where they trapped 110 nanometer particles, okay, with very intense laser beams focused in a diffraction limited setup to a very tight focus spot. These polystyrene particles, because of the high local intensity, they only survive for 25 seconds. When there was 110 nanometers. If they went down to 85 nanometer or 38 nanometer particles, they were killed so quickly that they couldn't even observe that they were trapping them. So here's the challenge. How do you trap something that's so small with reasonable optical powers that you don't have to burn them, basically? Okay, so the approach that we use is to use aperture trapping. And with aperture trapping, a typical aperture also has transmission, which scales as the fourth power of the radius of the aperture divided by the wavelength for an aperture in a metal film. Okay? By adding a particle into this aperture, effectively you're making the aperture bigger. So you have more light that goes through. And this more light that goes through is a huge change in the photon momentum. So this photon momentum acts on the particle to pull it back into the trap and allows it keeps the particle inside the aperture. Okay, so this is the experiment. It's a very simple setup. Essentially, we have a metal film with a single aperture now, and we have a micro well with a bunch of polystyrene spheres floating around, and we shine light through this aperture, and then we detect the light on the other side. We detect the transmitted light. And when more light goes through, this is when you have your trapping force. And so seeing a trapped particle is just equivalent to seeing more light go through. This is what an experimental measurement looks like. This is the light. These jumps are particles being trapped. 100 nanometer particles, polystyrene particles, okay? If you up the intensity, they get trapped for longer times. At some point, under a milliwatt, you can trap them almost indefinitely for 100 nanometer particles. It's important to stress that these effects are not perturbative. This is not the gradient force trapping, okay? These effects actually result from the fact that the particle has a very strong perturbation, it creates a very strong change to the local electromagnetic environment inside the hole. To prove this, you can do a calculation for the forces using the traditional gradient force method, where you calculate the fields, and then you look at the forces acting on the particle after you've calculated the fields. Or you can calculate the particle at every single position inside the hole and calculate the force on the particle at that position. And if you compare these two curves, one for the perturbative method and one for this Maxwell stress tensor analysis, the full comprehensive analysis, you see a much larger force than when you have the comprehensive analysis as compared to when you have just the perturbative analysis. And this force is actually, you have to integrate this force to get the energy potential. So it's actually even a bigger effect than is being displayed here. It's not just a factor of 2. It's much more because it's the integration of this curve. Okay, so how far can you push this? Okay, we come back to our double hole trap, okay, a double hole structure. A double hole structure allows for this local intense field at the cusp between these two holes. By using this double hole, we've recently managed to trap 12 nanometers, this is being published now, 12 nanometer particles inside this in the cusp of this double hole structure. So you can get down to 12 nanometer particles. So when you're talking about 12 nanometer particles, you can start to think about trapping smaller and smaller things, okay? This is just showing you some of the steric hindrance properties of this double hole, which is maybe not so interesting. But basically, you can imagine that if you want to trap a 20 nanometer particle, you don't want to use a 15 nanometer gap because that's just too small for the particle to fit into. You probably want to use a 25 nanometer gap. You don't want to use 30 nanometers. It's not small. It's not the smallest gap that you could use. So there's kind of an optimal size of gap. So recently, we've been able to trap a single protein, bovine serum albumin. Okay. So this protein has a 3.4 nanometer hydrodynamic radius. This is basically what it looks like. So this is our trapping events, and you see a huge jump in the transmitted intensity when you trap. Okay? So clearly you're trapping. But we also see this weird double step feature. Okay? So we see trapping, and then we see sometimes you go back down to this trapping level. But if you zoom in on these positions over here, every time we see this double step. Okay? So you see this this initial state and then a higher trap state where more light gets through the aperture. And we're thinking about what this could be from. And it turns out that bovine serum albumin is a protein and it can fold and unfold. And this folded state has a lower polarizability than the unfolded state. So the particle, basically the trap will act to unfold the protein because it wants to have the highest polarizability, right? That's the one that has the highest trapping energy. So what you end up is you first trap in the folded state, and then you unfold the protein, and that's this more light goes through your aperture then. So what this trap is doing is not only trapping the single proteins, but it's actually unfolding them. Okay, and more recently we've proved this. I don't have the slide for this. I'll show the slide tomorrow. But we've proved this by changing the pH of the solution and starting with the naturally unfolded protein, and then you don't see this double step. Okay. I'm kind of running out of time, but I'll just go over these last couple of slides quickly. These nano hole arrays, you can get enhanced extraordinary optical transmission through a hole array, but you can also get extraordinary optical transmission through a single hole in a waveguide geometry. And essentially, what ends up happening is you excite the evanescent modes of this waveguide, and they're bound at the surface. And this builds up a lot of electromagnetic energy around the aperture. And this energy will then transmit through the aperture in the metal film. This is a simulation that we did for the microwave regime. But And people have actually done this experiment in the microwave regime. Recently, we've transferred these ideas to near-field probes, so down to the visible regime. And these near-field probes, they're basically glass fibers that are tapered down to the point where this cusp, this end part of the glass probe is very much smaller than the wavelength of light. And you overcoat these with aluminum, and usually you just collect the light through this tapered fiber, and you use the tapered fiber close to your sample to collect light directly from your sample. So that's the principle of an aperture near-field scanning optical microscope. A problem is that you don't really get much transmission through this aperture if it's much smaller than the wavelength of light. So if you want to get high resolution, you're going to be dealing with very small photon numbers, okay, which is really bad for example, looking at single molecule fluorescence. Okay. So we've managed to create this resonance structure for this tapered aperture by tuning the size of this aperture over here. We first create an aperture in aluminum, then we overcoat with gold, and then we create another aperture in gold. And so the smaller aperture defines the resolution of our probe, and this larger aperture defines the resonance peak in the transmission through this aperture. And by doing this, we can get 100 times increase in the transmission through this aperture. Another way of looking at this is an aperture which has a 45 nanometer diameter has more transmission than the traditional near-field aperture probes with 110 or 120 nanometer size apertures. So in other words, if you're trying to get really high resolution imaging of single fluorescent molecules, you want to use a 45 nanometer aperture, you can get around 60 nanometers resolution of these single fluorescent molecules on a surface, right? But you get the brightness associated with 100 or 110 nanometer aperture. Okay, so that's a huge boost in the brightness. Okay, so just wrapping up here, for those of you who are interested in some of my work and other people's work in the area of extraordinary optical transmission, we have a review paper that kind of surveys the field that came out last year. And I'd just like to thank all my collaborators. That's my group as of last year. We have updated photograph, which I should probably put on there at some point. And these are some of my collaborators. Thanks.
All right, we're going to have some time for questions. Anyone? Who's first?
So this goes back to much earlier in the talk. You had a gold interlayer, and you put molecules inside the hole, and you saw a shift. You can miss the explanation. Why did it shift?
So this transmission through the hole arrays, there's sorry? Oh, sure. I don't think I have sufficient figures for that. It's going to take forever. Okay, so the figure doesn't really explain very much. Just that we use a sol gel process to overcoat with silica. So we basically block off the top layer of the gold. Now, in this hole array geometry, you have enhanced transmission that comes from light scattering off the hole, coupling into a surface plasmon, and then going through another hole in a resonant way, right? But there's also the optical properties of the light actually transmitted through the hole, okay? And these depend very much on the mode characteristics of the aperture itself, okay, as a waveguide, okay? So you can, it's a good approximation for relatively thick films to assume that there's only one mode inside this aperture. And if you change the dielectric environment for that mode, it's going to change the propagation constant in this aperture. And it's going to influence, for example, it's going to influence the propagation through the aperture. It's going to influence the reflection at the edges. It's going to influence the coupling of one side of the gold film to the other side of the gold film. And so basically, it's the coupling, it's the transmission channel is changed. And that
Similar to changing the size of the hole?
Yes. And changing the size of the hole, it's well known, will shift the peak as well.
Okay.
Yeah.
Very small change in the size of the hole.
Yeah, very small change in the size of the hole. Yeah, yeah.
Did Josh just have a question or you give up?
Yeah, so when you were trapping the protein molecules, how do you know that you're not trapping more than one?
Okay, so that's a good question. So we do experiments with single particle silica spheres down to 12 nanometers, okay? And we look at the intensity changes. And then we do the same experiments with the protein, which is about, along its longest axis is 9 nanometers, okay? And we see comparable transmission changes, okay? Now, you could argue that we're seeing dimers, okay? But then we always see dimers, because that step is always exactly the same. We never see, so there's no population there. So it's very unlikely that we have a solution entirely of dimers. If it's entirely of dimers, you expect to have some part of the population will be monomers, some part will be trimers, or something like this, right? There's nothing that we've done special to the solution to make it dimers. So also, we see this unfolding. Initially, we thought this unfolding, this double step, was coming from having a dimer in there, like trapping one and then trapping another one, right? But then we'd always see this co-trapping event. And then when we tuned the pH, we found that we didn't see this double step. And tuning the pH is basically unfolding the molecule. Okay, so we're pretty sure that this double step comes from the unfolding of the molecule. Yeah. The transmission won't be very high. Actually, the transmission can still be high. It's kind of like extraordinary optical transmission, except instead of having an array of holes, I've generalized the concept to a single waveguide, okay? So the walls of the waveguide kind of act like the periodicity of the array. Oh, okay. So this figure kind of shows it well. What ends up happening is the light comes in, it scatters off of this aperture. That creates a magnetic dipole. The magnetic dipole radiates into this mode that's close to its cutoff. It radiates very efficiently into this mode at the resonant wavelength. I can't really explain in a short amount of time the physics behind that, but essentially, at the cutoff for a TM mode, at the cutoff of a TM mode in a waveguide, the ratio between the electric field and the magnetic field goes to 0. In other words, the admittance goes to infinity, which means that for any small amount of electric field in the aperture, you have an infinite amount of magnetic field. And that means that you have an infinite polarization of the magnetic dipole. That's the aperture. It acts like a magnetic dipole. And so basically, it becomes infinitely strong. Okay? So you can get a huge amount of transmission through this aperture at the cutoff of one of the modes. It's a little bit complicated to understand that, but if you use Bette's aperture theory as formulated for microwave regime, and you take into account 2 modes, the propagating mode and this cutoff mode near cutoff, you get very accurate representation of the extraordinary transmission that you get through this. So it's actually not really extraordinary compared to Bette's aperture theory. It just includes, because you can still use Bette's aperture theory, you just have to include the fact that this mode has an infinite admittance close to its cutoff. It should be close to, the size of the hole, you can make it however you want. It's just going to tune slightly the resonant wavelength. Okay, so yeah, the size of the hole will change the polarizability of the aperture, which will change the resonant wavelength.
One more question?
No, flow-through system, you're detecting only one entity?
So far, yeah. So far, we just use sort of very canonical, streptavidin, biotin type.
Is there a way to do multiple?
Yeah, so that's what we're looking at doing. So you can think of ways to multiplex this, and this is kind of part of the challenge. A simple thing with these silicon nitride membranes is you can have windowed silicon nitride membranes. So each window could be a separate fluidic channel, right? So that's a very simple way to do it. But there are other schemes that we're looking at, like cross-patterning and stuff like this, that allow you to address. And there's a lot of functionality that can come there.
Also, I guess, along the lines of trapping one single protein or single molecule, it's reduced down to concentration. So
Yeah, actually, that's one thing I didn't really talk about. But this trapping, this trapping of single proteins, it's actually, the thing that I didn't really say is this is an amazingly sensitive sensor. Because this is a single protein that you've sensed. Okay, just by looking at the light transmission, you've observed a single, this is the signal to noise ratio. Actually, you can look at this is not noise. These fluctuations are the particle moving around in the trap. This is the noise of the system. You see the fluctuations on that? That's the noise. This is noise that's coming from the particle moving around, okay? So our signal to noise ratio is huge here for a single protein. So the things that we're interested in doing now to take this further is to combine the microfluidics and do single molecule binding. So you get like anti-BSA, for example, and bring it in and bind it and look at binding at the single molecule level, right? So that would be the type of thing that you could do is to extend this. Because even if you're not trapping, you have enough signal here to monitor, single molecules coming into the aperture. Okay, I guess you said that was the last question, so,
Yeah.
so everyone's obeying your.
Thank Reuven again.